speaker, Maxime Taillardat. Evaluation probability forecast of extremes using continuous random probability score distribution. That's almost half the talk.
Yeah. Thanks, Tobias, for the introduction, and thanks to the organizers of this residential program and the two workshops. So my name is Maxime Taillardat. I'm working in Météo France, so the French equivalent of the Met Office, and I'm working in the statistical forecasting and verification team. And I want to talk about the evaluation of probabilistic forecast, still with the CRPS, as Romain introduced before, but maybe more for extreme, and maybe more in an informal way from a mathematical point of view. So I'm gonna do things maybe very strange, but let me show this, and we will see them together. So first, a brief recall or a brief information of how the evaluation of weather forecast is made. Typically ensemble or probabilistic weather forecast. This evaluation has to be statistical. That is to say that, for example, if it rains tomorrow in Reading, and if my probability of rain tomorrow in Reading is of, for example, 40%, it's typically nonsense to say the forecast was good and the forecast was wrong, okay? Because it is a probabilistic forecast. So the evaluation of this type of forecast has to be made on an extended range. So we seek for several attributes in this forecast. First, the reliability, also known more or less as a calibration. This is the accordance between forecast probabilities and observed frequencies. Okay, so if I forecast a probability of 40% of rain tomorrow in Reading, I have to observe 4 on the 10th. Okay, 4 on the 10th. A rain occurrence in Reading from one day to another. So the second thing we seek to evaluate is the resolution of our forecast, also non-discrimination. It depends on the point of view of the forecast and the observation. It is the ability to differ for a climatological forecast, because by definition, a climatological forecast, a static forecast, is always calibrated or reliable. Okay. And last, the sharpness. It is getting the least dispersed forecast from a probabilistic point of view. It is the only attributes only related to the forecast itself and not the accordance between forecast and observations. So there are a lot of things to say about the way to make and to increase the quality of ensemble forecast or probabilistic forecast. Knighting said we have to maximize the sharpness to this forecast subject to a condition of calibration, for example. And for extremes, this is quite different between statistical standard evaluation and extreme evaluation, in the sense that the notion of reliability disappears, because for extreme events, the notion of observed frequencies it's also collapsing. That's why we have to be careful of what can be done for extreme events. So that's Sebastian Lerch called the forecaster's dilemma, and he take as an example the forecasters of the Italian earthquake in L'Aquila in 2006, if I recall well, who was blamed for a forecast which is a well-known case. So to evaluate in a same score or with the same quantity these attributes, we rely on proper scores, proper scoring rules. So a well-known or widely used is the CRPS. It is a distance-sensitive scoring rules. Okay, contrary to, for example, a likelihood or a log likelihood, which is a local scoring rules. So here I provide a different way of writing the CRPS, provided that the forecast distribution is continuous, okay, and the outcome, the observation, is coming from an unknown distribution G. So as Romain said before, the CRPS is a proper score. That is to say, the expected score rewards, in average, always the forecast issued from the same distribution of the observation, okay, which is unknown in practice. And also in practice, we are compare forecasts with some of empirical quantities, so empirical averages. So with some of sum and average of CRPSs during time and for several locations. So they're kind of hidden ergodicity or something like that between expectancies and averaging, empirical averaging. So, as we can say, so we measure or we compare forecasts based on averaging proper scoring rules. But what happened? The things that happen when we do an averaging is that extreme events are kind of completely drawn in the observation sample. So in the literature, we try to propose what we call proper weighted scoring rules. This is a kind of adaptation of the scoring rules with an emphasizing on some region what we have to interest, and especially for extreme events, the tails of the distributions. So, for example, here I provide an example of a weighted CRPS where W, the weight function, is a strictly positive function with a finite integral. And so I precise that we must, the W, the weight, must specify ex ante, okay, unless you can be tempted to hedge your forecast or to cheat, in other words, okay. So there are also version of weighted log likelihood, for example, also. So we could say that finally the work is done with extreme event evaluation and proper scoring rules, but there's a very bad property of this CRPS and weighted CRPS for extreme events. And I will show you a little slide on extreme value theory, and I will talk about tail equivalence. So the tail equivalence is a comparison between the tail behavior of two different distributions, okay, F and G. And what is a tail equivalence? First, let's imagine you have two distributions, maybe a normal or a variable one, with the same upper endpoints, okay? Which can be the infinity, okay? For the normal distribution, the upper endpoint is infinity. And we can say that F and G are tail equivalent distribution, whereas if their survival function 1 minus F over 1 minus G, the ratio between the survival function, is a real constant. Okay, positive. So, and when we want to apply the extreme value theorem called the Pekan-Balkemadian theorem, so we assume that F is in one domain of attraction and G is another domain of attraction. Okay, these domains of attraction are led by a gamma, which is the tail parameter of distribution, and we have this theorem, so which says that the probability of threshold exceedances can be approximated by a Pareto distribution whose tail parameters depend on the domain of attraction. Okay, for people who are not very familiar with extreme value theory and domain of attraction, let's imagine in classical statistical framework you can use the central limit theorem, saying that the mean functional of a random variable tend to a normal distribution under some condition. In fact, the Pickens-Balkema theorem says more or less the same. It's not the Pickens-Balkema theorem; it's the Fisher-Tippett-Neelenko theorem. But anyway, in fact, this is the same framework for not for the mean functional, but for the max functional. Okay, and the extreme value theory theorem says a max functional can go into 3 different domains of attraction. Okay, so there's not one low limit, the normal low limit for central limit theorem, but for extreme value theorem, there's 3 different low limits. Okay, so and there's an equivalence with the tail equivalence property, which is expressing at the equality of the tail indices between the tail index of F and G. So we can wonder whether the CRPS is able to discriminate a difference in tail regimes between 2 different distributions for a set of observations. So is the CRPS, or the weighted CRPS, is a tail equivalent proper score? In fact, this is not the case. So even if they are designed to focus on extreme events, the CRPS in their weighting counterparts are not tail equivalents. In other words, for any positive quantity epsilon in average, I can always find a distribution close to the 2 distribution, but not lying in the same domain of attraction, which is epsilon close in average to my CRPS. Okay. So let's imagine you have a true forecast, a true belief, perfect forecast with a kind of tail. Okay. Tail forecast. I can exhibit a forecast completely with another tail behavior, but approximating in average the same CRPS, as close as I want. So even if we want to weight some proper scoring rules, they are unable to discriminate properly forecasts with different tail weighting. So we've shown it for the CRPS, but in fact this is a more broader theorem shown by Bremer and Strokorb 3 years ago, saying that proper scoring rules are not suitable to distinguish tail properties, nor any max functional. So for estimating the tail index with a M estimation, for example, by minimizing a score, it can lead to unstable results, which is a kind of a paradox. So what can we say? What can we say? What can we do? We are like struck by theory. So we try to make a benchmark and simulation to try to understand what can we do with all this bad news. So first, a quick recall on prediction space. This is a triplet with a sample space, a set of events, R, and a probability measure. So a space that we compute probabilities in a nutshell. And I define different set of events, okay, so sigma algebra, okay, and in the context of weather forecasting, we can say that the AI are generated by a random variable delta, and delta is let's say the state of the atmosphere at a given time, okay? And nature choose in delta to compute, to provide an observation to the people. So we compute simulation using a hierarchical model based on gamma exponential mixture. So where the gamma is a gamma law, and the compound the conditional y law of observation on gamma is an exponential law. This is a very nice benchmark because the unconditional law of y is a Pareto law. So with the Pareto law, the extreme value theory applies whatever the threshold. So it's very convenient to us to work in this kind of framework. So at each time t, an observation of the a priori knowledge of the system of the atmosphere is drawn with a little delta t, and yt is drawn independently in a exponential law. And we have built several forecasters. So the ideal forecaster, where the forecast comes from the same distribution that the observation. We have the climatological forecaster, okay, the unconditional one, so all Pareto distribution. We have a lambda-informed forecaster, which is a mixture between the unconditional forecaster and the perfect forecaster, okay, and the alpha and the lambda-informed forecaster is using, in fact, an information set I call here B lambda, which are nested, okay. So there are a stochastic order in lambda between information set and the lambda informed forecaster. And then we have also an extremist forecaster, which is only the perfect forecaster, the ideal forecaster with another parameter A, controlling the forecast bias. Okay, so which is interesting in this benchmark is that the ideal in the climatological forecast does not belong to the same different regime, because here for the climatological forecast we have a Pareto distribution, which is in the domain of Fréchet distribution, and here we have an exponential distribution which lies in the Gumbel distribution. Okay, so gamma equals 0 here for the limit law. So what can we do in fact? So let's play a little. What is available for a forecaster when we want to make verification? We have observation, okay. We have the observed realization of the atmosphere, of nature. We have the distribution of time t, and we know the unconditional distribution. This is a climatology, okay. We assume we know the climate, even if it's changing. And for sure, we are able to compute the CRPS for a time t. So let's play. In this context, I can build two different empirical cumulative distribution functions. I can take all the CRPS that I compute. Instead of averaging them in a classical way, I will build an empirical CDF coming from my CRPS values. And I can also do another thing which is quite weird. I will compute CRPS taking forecast from one location and one time, but with an observation completely unrelated to this location and this time, but coming from the same unknown climatological distribution G. Okay, so here we apply a pi, a random permutation on our CDF. In fact, applying this permutation breaks completely the coherence, the consistency between forecast and observation. Okay, this is completely normal because we compute score on quantities, forecast and observation completely unrelated to each other. But for the climatological forecast, which is always the same, because it's always G, whatever the time, the fact of shuffling observation do not change these two empirical quantities. So the distribution S and S star are the same. And an interesting fact is that when we try to compute, so when with random permutation, when we try to compute for our different forecasters, the difference between the two empirical CDFs, the true coming from the true CRPS and the shuffle observation CRPS, we can see, in fact, so the distribution is nearly the same for the climatological forecaster here on the QQ plot, here on the PP plot here. We can say that there's a really stochastic order. The dominance of the forecast is kept among all the calibrated forecaster. Here you have the climatological, the 0.25 informed, the half informed, the 0.75 informed, and the ideal one, completely informed. There's a kind of stochastic order, whatever the shuffled CDF. Okay, which is quite strange, in fact. For those who are familiar with Murphy diagram for point forecast, it is more or less the same feature that they are called dominance diagrams. Okay, and it permits to see in which area of my distribution one forecast is better than another. Obviously, here for high value of the CRPS, so my extremist forecasters are better than an ideal one, but it's completely artificial, okay? Because the bias forecaster are crying to the wolf, okay? In fact. So this is the first funny thing I want to say about this, and the second and last thing I want to say about this, and we can also apply extreme value theory of the distribution on the distribution of CRPS itself. Conditionally to an alpha T, we have this theorem, the Duplicant-Palkema theorem, where the survival distribution function of the CRPS given a high observation leads to a Pareto distribution whose tail index is gamma T. But for the unconditional E, for the climatological forecast, the limit load of the distribution of the climatological forecast as a random variable, okay, the CRPS as a random variable given an high observation, is led by the gamma index of the observation. So in fact, we have a theorem from the calibrated and unconditional distribution, and what you want to take is a counterpart of this theorem. So let's say we have a theorem with a limit law for an unconditional distribution subject to calibration, and if we take the contraposé, the counterpositive part, maybe for the ideal forecast, this theorem collapses. And the more it collapses, the more we are informed subject to calibration. So to see this, we can compute a kind of distance. It's like we are kind of in a framework of test hypothesis, but it's not the same design. We can try to compute a distance between the low limit and our CRPS distribution that we have in practice. And in fact, under calibration, I don't explain auto calibration, but under calibration, large value of my statistic are related with more or less very small p values, and we have a kind of model unselection tool. Okay, so if I construct the index with both p-value or the value of the statistic, I have an index when for 0 to 1 and 0 for the climatological forecast. And when we built this index for different threshold here of the climatology, we can see that again, extreme forecasts are taken apart, but among all the calibrated forecasts, the ideal forecast is still the best. So we have fine with applying extreme value theory on the score itself as a random variable, kind of one or two funny tricks, in fact. So, and this is also an example coming from real CRPS data, coming from a former study. Here you have a rock curve for a pretty high threshold of 15 millimeters in 6 hours, and we can see here that the value, so the Peirce score here, the upper left corner of the rock curves are more or less related with the value of the index for very high quantities. So to conclude, my talk was just a first attempt in order to open new ideas in this field of research. So instead of considering score average, maybe it's better to look at score distribution under some assumption. So I'm here to plant a seed in your heads. In fact, such a procedure may be tried with other scoring rules and other statistic. The field of possible application can be the comparison of calibrated forecasts themselves, or the comparison of raw forecast version with the same amount of miscalibration between, for example, a former version of weather forecast between an update of the weather forecast, for example. And if you want to go further, we have a paper and an air package. And I still need to thank my co-authors for this work and see which is very strange, I admit. Thanks a lot.
So, any question?
In fact, yeah. In my benchmark here, I have some lambda informed forecaster, which has a mixture between the unconditional and the perfect. Okay, and I vary lambda. Okay, lambda equals 0 is the unconditional forecaster, the climatological one, and lambda equals 1 is the perfect forecaster, and there are stochastic ordering in lambda.
About this PP plot, I was wondering whether we can prove that the curves are full order, or at the moment it's more like an observation.
I think this area between the two curves is more or less for calibrated forecast related to the loss of information. And there's a paper of Holtzman and Clark, maybe five years ago, stated that there was stochastic order among calibrated forecaster, and this order is completely driven by the size of the sigma algebra of the information set. And when the information set are nested, so what each forecast dominates each other. So I think that's why for the calibrated forecast, the curves are not the curves are not crossing, but I'm not enough skilled to prove that formally.
Yeah.
So is it, I mean, I might have just missed the main point of your talk, but so effectively to break this English Foucault theory or whatever, I can't remember the name, but the suggestion is, of course, to look rather than at the mean, you look at the distribution of the CRPS. Mm-hmm. And this is what you're doing, does this not suggest to look at the extremes of that? Is it not okay to just focus on the extremes? I mean, this is just what you would say.
Yeah. In fact, we are interested in focusing our view on extreme events, and so here this figure is not about extreme events evaluation at all, but this theorem is, because here, in fact, when we apply extreme value theory, here, in fact, we have the distribution of y very high given y n of I. So here, in fact, we have kind of transformed the theorem to have the distribution of of score given high observation.
Yes.
And in this context, we are focusing on extreme events. In fact, the X here, so in fact, the index here, this is U, okay? This is U. So here, the more close to my extremal observation I go, I have a kind of continuity of my index. So.
Yes, thanks.
I was wondering about your first statement that when you said that if you take a given predictor, then you can find the surface for a prediction with a definitive behavior. And will you still have that if you were to take different scores?
Yeah, yeah. That was Jonas Bremer and Christine Stroker proved, in fact.
Okay.
You can take all proper scoring rules. They are all the same the same fatality. And the worst is the any max functional. So if you want to the worst is this last property, no any max functional, because let's imagine you want to estimate the tail index of your distribution using, for example, maximization of the log likelihood. The log likelihood is a proper score. So your estimation can be unstable in the sense that you can be epsilon close to the maximum of log likelihood, whereas you have not the good tail index.
If that's not the case, let's thank the speaker again.
Yeah.